Okay, Łukasz, so please start.
Yeah, dlaczego ja?
Why not?
Okay. Good morning, everybody. I hope everybody is already connected, and we are having a pleasure to open this year's seminar on fundamentals of physics. That is a continuation of a seminar which goes on in the Joint Institute of Physics and Center for Theoretical Physics since many, many years. And we have a custom that the first talk each semester is given by one of the individuals responsible for the seminar on the side of the faculty. And today it's the pleasure to introduce to you Professor Marek, who will be talking on the relation between physics and mathematics. And we are planning to devote to this year or this semester seminars to truly fundamental problems of theoretical physics. A list of those topics has already been sent to and made public, and kindly choose what you want and communicate with Professor Witlin, who is our bookkeeper, and he will be assigning you a proper time slot on our seminars. So today the talk is on the relation between physics and mathematics, and the speaker is Professor Marek Kuś. Marek, the screen is yours.
Thank you very much. Good morning, everybody. It's a real pleasure and honor for me to start this semester seminars. And because we plan to devote the whole series, as Łukasz said, to some fundamental problems of mostly of theoretical physics, but not only, but with an emphasis put on the, I would say, mathematics, which is in this physics. Okay, so mathematical tools and mathematical reasonings, which are actually important for this particular topics which we want to discuss. You know the plan of our seminars, so the collection of topics we want to address, and you understand from that we will be talking about the different aspects of this applications of mathematics in physics. For example, there are many, I would say, parts of mathematics or which apparently are useful in physics. From the mathematical point of view, okay, mathematics is unique, but it has several, I would say, compartments, and these compartments are sometimes very, very far one from another. But apparently many of them have astonishingly interesting and successful applications in physics. So the topic of my today's talk is on the relations between physics and mathematics, and this is a huge topic. Okay, so you can easily devote several hours discussing various aspects of these relations. And the existence, the properties of these relations, and so on. Because it's so vast topic, I will, on the contrary, I will confine myself to a very short introduction to this problem. Also, in hope that it will raise some questions, or it will be a good starting point to some discussion during this hour, during this meeting. So I would not concentrate, or I will not touch all possible aspects of this problems, which are somehow indicated in this title, but only to very few, which I think are very characteristic for the whole discussions about the relations between these two areas of science. Okay. So the questions we have to answer before entering the topic of relations between these two areas is first, what is physics? What does physics describe? On the one side, and on the other side, what is mathematics and what is mathematics about? What is specific in mathematics? Everybody feels that mathematics is some, so there are similarities between something which we call exact science or natural sciences, maybe less better, like physics, chemistry, biology, and mathematics, which is usually or obviously called also a part of science, it's a little bit different. Okay, so let's try to also to elucidate what are these differences between mathematics and the rest of science. So what is specific in mathematics and whether it is really different from other sciences. And the main topic of our meeting is, why is mathematics important to physics? That this is important, it is obvious, okay? You are already after several years of studying physics, and actually what you are doing, except probably in laboratories, but also in laboratories, was to apply mathematics to solve physical problems. So why it works? Why we actually what we called theoretical physics is actually so mathematical, okay? So it's hard to understand that. I don't think that we'll find an ultimate answer on this question, but let's us at least formulate the problems in more, I would say, clear way. So what is physics? What is the physics is, roughly speaking, and very, I would say, straightforward definition is that physics is the study of matter, or maybe rather fundamental constituents of matter, it's their motion and interactions, okay? So, I have a citation here from Maxwell, from his book Matter and Motion, which was issued in 1878. Who actually describes the physics as in the following words. Physical science is the department of knowledge which relates to the order of nature, or in other words, to the regular succession of events. So this is something which we will meet in the further development of this talk. What is emphasized by Maxwell, that there are some regularities in the phenomena which are investigated by physical sciences. And this is very important also from the point of view of applicability of mathematics to this, to physics. So what is most important, I would say, what differentiates physics and mathematics, that physics is an experimental science. The practice of physics includes controlled experiments. The goal is to discover these regularities, which we call laws of physics, and this in the hope that they will allow us to first to identify and understand causes and effects of states of matter, and that they also form the background or grounding for other sciences, like, for example, chemistry or biology, that deal with something which we can call higher structures of matter. Okay, so we reserved this, we preserved this name of physics to investigations of very elementary constituents of matter. No, nowadays elementary particles, fields, atoms, and etc., and give to give the ground for something which is more complicated, and it usually which is not a, I would say, direct, indirect interest of physics, like for example, biological structures or very complicated chemical structures. What is important is that the laws of physics usually apply to certain limited situations, although obviously our aim is to cover as much as possible, so as large as possible area of physical reality. And what is important about also these laws which we discover, that in the course of development of physics, they are often replaced by more general laws with a greater range of applicability. It usually does not mean that the laws which we accepted until this revolutionary moment when we have to change our theory are completely wrong. No, they are usually working very well in these areas in which they actually were constructed, or to describe of which they were constructed. So classical mechanics is also a very good theory, despite the fact that we know that we have now to extend it to, for example, to the bodies moving very fast, and this is a relativity theory, or to very small objects, and this is quantum mechanics. But for our purposes, for the most of the, I would say, mundane goals which we pursue during our life, so classical mechanics is still a valid theory. So this is the last point, that all laws usually remain in use in application to the areas for which they were formulated, although they usually lead to an approximate description compared to new laws. So more, so they are less accurate than the new laws, but usually within the margin which of this approximation is small enough to apply them to the problems you want to attack. So this is very rough, I would say, idea what physics is and what physics is about. So let's then change to the problem of what is mathematics. So playfully, I would say that, but to some extent very accurately, is that mathematics is what mathematicians do, okay? And what they do, and they do the very different things, okay? So they do algebra, geometry, calculus, combinatorics, number theory, theory of probability, etc. You can enumerate many other areas of mathematics. So what do they actually, or these areas of mathematics, have in common? That could be objects of interest. Oh, so this, I would say, set of objects, or the universe of objects which are object of interest for mathematics are very wide, okay? Because these are, I don't know, lines, points, pentagons, hexagons, and so on one side in geometry, okay? In calculus, there are some velocities or rates of change of functions, rate of change of functions, and so on. In combinatorics, there are sets of finite cardinality, finite number of elements, and the problems is what we can do is that in number theory, these are numbers, okay? Natural numbers, which we know what they are, intuitively know what they are, and what are the properties of this. In the theory probability, there are some, I would say, something like expectation values and so on. So they're completely different in nature. All these objects are completely different one from another. So it is very hard to identify mathematics upon the identification of the objects on which it is concentrated. Okay. So what is maybe more, I would say, appropriate to characterize what is mathematics is to consider the methods which are used in all these areas. And the methods are to some extent really similar, and we will talk about this a little bit later. And the third thing is a character of statements which are provided by mathematics. So we can usually think of mathematical statements as some established and truth. Okay, so they are certain. They are, I would say, not restricted by time or space. Okay, they are universal. Okay, so these are probably the ways which we can follow if we want to characterize what is mathematics. Sure. So what are the origins of mathematics? Are they different from the origins of other sciences? So definitely at the beginning, I would say the root of all mathematical concepts lies in observations of nature. So whether they are geometric, for example, positions and shapes of various physical bodies, or quantitative, which concerns sizes, weights, and similar properties of objects. Okay. But on the other hand, we know that mathematics is also somehow consists of something which we call pure speculation. So once we establish some set of objects or concepts rather that we can investigate from the mathematical point of view, then we manipulate this in certain manners. We made some manipulation on this object without referring to any external experience, and then we produce new sentences, new truths, new mathematical truths. So what we commonly attribute to mathematical results. So first, what I already said, that they are certain. Okay, in a sense, we believe that once proven that they are true forever. Okay, so that means that they are really definitive. Once proven, they do not need to be changed or amended or anything like that. The fact that they are true can be confirmed or tested by mental processes, by simply analyzing this in our minds, okay? And moreover, then they do not require the existence of physical reality. So they are true by themselves without any important or needed test coming from the outside world, okay, outside to mathematics. So from this point of view, from the point of view of, I would say, physical reality, they are alien to this area, this physical reality. So this is somehow probably the meaning of of the sentence, which are sentences which I took from Maurice Klein. That mathematics is a body of knowledge, but it contains no truth. Okay, so it contains mathematical truth, but this truth has nothing to do with this truth, which are truths about physical world. So the truth can be attributed only to statements about physical objects. Otherwise, not interesting and empty from the point of physics. Okay. Okay, so let's come to this three ways of investigating what is mathematics about. Okay, so first question is, what are mathematical objects? So there are several, I would say, attitudes to this rather philosophical than mathematical problem, but philosophical. Out in modern formulations, they could be roughly divided in such three main approaches. Okay, one which is probably shared by the majority of mathematicians that mathematical objects exist independently of physical reality and of us. These objects are in some sense perfect, contrary to physical objects. For example, in physics, there are no ideal spheres, straight lines, etc. But these are definitely the concepts which are used in mathematics. So they must exist somewhere else, okay? Because they do not exist in physical world. The mathematics consists of finding truth about these objects by specific methods which are characteristic for mathematics. And so, in a sense, we discover this by trying to approach this world of this Platonic world of ideas, and by intuition and so it depends on the philosophical attitude, or remembering somehow back, remembering our previous contact with this sphere of abstract objects, we can prove mathematical statements. So this is as I mentioned. So this is probably more or less so pronounced, so expressed way. The opinion of, or this vision of mathematics is shared by many mathematicians. So in contemporary or in modern times, the prominent representative of this attitude was fantastic mathematician and logician Kurt Gödel. Okay, so for him there were some ideal objects existing, not in our physical reality, but definitely existing somewhere. Okay, I would say that on the somehow opposite side is something which we called intuitionism, and which claims that mathematics is the result of the constructive mental activity of human. It does not discover objects and principles existing in some reality, but rather constructs them. Okay, and such a mathematical object, which is constructed by a mathematician, the fact that it exists means that that object with those properties can be constructed. So for a constructed soul, you have to say how to construct it, okay? How to approach it by construction. So this is, I would say, this has some disadvantages, this approach. For example, one of the main ideas of this approach is that the law of excluded middle, that either A or its negation must be true, is not applicable in mathematics. So it means that it somehow disqualify all the mathematical results which are obtained by so-called principle of contradiction. Okay, so if you prove that something that the non-existence is not possible, so it does not mean that the object exists. So this is very hard to be intuitionist. But okay, but this is really something which was very popular, or not very popular, but which was popularized by Prover and Hating at the beginning of the first 20 years of the previous century. And this was, I would say, some answer to the problems. What is mathematics about? Okay, something which is, I would say, most common now in treating mathematics is something which is called logicism and Okay, so sometimes formalism, also there are subtle differences between these two notions, which mainly says that mathematics reduces to logic. So the mathematics involved drawing logical conclusions from definitions, other theorems which were already demonstrated, and the starting points are the sets of more or less arbitrarily accepted axioms. Okay, and if you look now how the mathematics is taught, it is usually so that you start from some set of sentences or statements which are axioms, and then you derive some properties by purely logical reasoning. Okay, so we accept some rules of logical inference and then apply it to the already proven sentences to produce new mathematical truths. What is very important in this important part of this mathematical production of truth is introducing new definitions. Okay, so without new definitions, there is no many things to be proven, starting only or limiting ourselves only to those concepts which are inside or which are included in axioms. Okay, but everything is here logical, so all reasonings are purely logical, and so the truth of mathematical statement is independent of our activity. So this is not that we have to construct something. These are definitive truths which are completely independent, whether we approach them, whether we construct them, or whether we think about them. But there are no outside objects to which mathematical statements refer. And I would say the most prominent representatives of this way of reasoning were probably Frege and Russell, okay, and at the turn of 19th and 20th century. And as I told you, this is the way which mathematics is now presented to us, or yeah, which is how mathematicians present their activity. Okay, but the origins of mathematics are definitely lying in the physical world. So the most primitive concepts of mathematics were definitely generalization and abstraction from nature. Then, after the development of mathematics, the new concepts alienated themselves from experiment in the physical world. So there is a problem. Why these new objects, which are defined by mathematics, investigated by mathematics, can be somehow applicable to this non-ideal physical reality? I told you that we understand this. There are no ideal objects from the point of view of mathematics in the physical world. Nevertheless, we can apply these ideas from mathematics to the physical reality. So the question is, why is the physical world mathematical, or maybe rather mathematizable? So maybe word itself is not mathematical, but we can mathematize it by simply describing this in terms of mathematical concepts. So whether this mathematizability is only the consequence of this origins of mathematics, which are, as I told you, definitely empirical and stem from generalizations of the observations of physical world. So, what are attempts to answer within the framework of these different concepts of mathematics I presented at the previous transparency? So first, Platonist says that physical objects are shadows of the ideal abstract one. So this is original idea of Platon. So truth about this ideal object somehow transfers to the physical world. From the point of view of intuitionism, so our intuitions which guide us in the construction of mathematical objects are rooted in observation of the physical world. So we are attempting to construct mathematical object just using the intuition which stems from our interaction with physical world. So it is maybe not so astonishing that they correspond to this, somehow correspond to this physical world. I would say that in the worst position is logicism, because there's no good idea why these logical operations which we perform on concepts, arbitrary in a sense constructed objects, could be applied to describe some physical phenomenon. The fact that mathematics is very important for physics was clear, maybe not transparent, but clear from the beginning of the development of both sciences. So I want to give you a few examples from different periods of history. So this is something which I like very much. This is citation from Aristotle, who actually wrote a book called Physics, and this is mostly about motion, which he uses definitely a kind of mathematical reason, which goes as follows. Let A or alpha A have moved B at the distance gamma in a time delta. Then in the same time, the same force A will move half of B twice the distance gamma, and in half of delta, it will move half of B the whole distance gamma. So this is the obviously English translation of the Greek text from Physics of Aristotle. And you can very easily, but Aristotle didn't have at his disposal the mathematical notation which we use now, but you can very easily translate it into nowadays notation. So if you say that this A is speaking about is a force, B is something which can be identified with mass of a body, gamma is the distance traveled by the body, and delta is time, which was used to this travel to conclude this travel. So you can write this statement in the form of the following equation, which is I would say Aristotle equations of motion. Okay, so you see that the velocity is proportional to the force and inversely proportional to the mass, which is, you know, from Newton's theory, it's not valid in general, because this should be second derivative, which is an abstract concept which was very difficult even in the time of Newton. But this is also not a very bad equation for the motion in the viscous environment. Okay, so this was already in antiquity, when this purely mathematical, I would say, reasoning like this one was applied to physical problems. So there is also very interesting, I would say, development of something which we would call mathematical physics, which occurred in 14th century in England, in Oxford. These are so-called Oxford calculators. I enumerated 4 of them with, I would say, the picture or the tomb of William Heytesbury, from which I want to cite the following passage. A moving body that acquires or loses uniformly its speed in any given time will traverse the distance perfectly equal to the one it would traverse in the same time when moving with a speed corresponding to its middle degree. This is also translation from Latin to English, but it's very easy to understand. The moving body that acquires or loses uniformity in speed in any given time is simply the body which moves with a constant acceleration, okay? Because it acquires or loses uniformly its speed. And it will traverse the distance perfectly equal to the one it would traverse in the same time when moving with a speed corresponding to a middle degree. So this is the first time when the concept of the mean velocity or average velocity appears. And this can be also written with our notation, nowadays notation says that in accelerated motion, the distance traveled is proportional to time and the mean velocity. So this is also a purely mathematical, I would say, formulation of a physical phenomenon. Okay. So now I don't want to go further in history with that, but obviously in Renaissance at that modern during 17th century when the modern science actually appeared. So these are few names of scientists who really applied mathematics. Mostly at that time geometry, especially it concerns Copernicus, Galileo, and Kepler, and then also geometry, but also something which we now call down calculus, so Newton and Leibniz. And there was no doubt that they used purely mathematical reasonings to establish some physical facts, okay, or physical laws. Moreover, it was clear that this application of mathematics in physics is something which is very fundamental. So it means that it is that this is, I would say, the heart of this science is the mathematics. So there is I have the quotation from Leonardo da Vinci, which is very early, so from 15th century. There is no certainty in sciences where one of the mathematical science cannot be applied or which are not in relation with this mathematics. There are many mathematics in this time, so that's why it is plural. So what was geometry, arithmetic. So and this was in his treatise about painting. Okay. So from this point, I would say mathematics became the only way to describe the physical world. Okay, so let's return to the question why we can use mathematics to describe the physical world, despite the fact that mathematics and physics are about completely different things. Okay, so they concern various. The point of their concern are completely different objects. Okay, whatever are the mathematical objects, they are definitely not physical. Okay, so the contemporary, I would say, formulation or discussion of this problem is contained in this famous paper of Eugene Wigner, which was also, I would say, the link to this paper was given in the advertisement of our seminar, which is called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. So he poses two problems there. Okay, so first is that the mathematics is simply useful, and this is very mysterious why it is so, because there is no rational explanation for it. And the second is that I would say richness of mathematical concepts and its usefulness in physics raises the question of the uniqueness of our physical theories. So they are connected, these problems, because if we do not understand the usefulness of mathematics, we cannot know whether our theories formulated in these mathematical terms are unique. Okay. Mostly because we test them on the very limited sets of data. Okay. So it is possible that something which we neglected when included in our theory will lead to completely different, I would say, physical theory, and mathematics is definitely capable of doing that because of its I would say, complications. So Wigner does not give an ultimate answer to these problems, but he tries to elucidate them in his own way. So he obviously poses the same question. So first, what is mathematics and what is physics? Okay, so mathematics, so he writes that mathematics is the science of skillful operations with concepts and rules invented just for this purpose. Okay, so usually the mathematics actually is alienated from the physical world, and it's really about the operations and manipulation on the objects which were invented in mathematics, within mathematics. Okay. So once again, he states what we already mentioned, that the concept of elementary mathematics were inspired by the entities and objects of the actual world. Okay, so this was this spatial extended objects, so the relations between their positions, also the properties like mass or weight rather, and shape and dimensions, and so on. But it's all on a starting point. Okay, further mathematics developed in the way which is not connected with the external world. So for this more advanced mathematical object, it's not true that they have some immediate connection or direct connection to physical world. So mathematics develops, I would say, from itself mostly by introducing what we already said, new abstract concepts by new definitions. Okay? So what is physics? So we know more or less what is physics, and we already thought that this somehow investigation of elementary constituents of matter. But what is important, what Wigner points out, that in a sense, miracles of this connection between mathematics and physics are also on the physical side of the problem. So, because physics is actually discovering the laws of nature, okay? But it is not at all obvious that such laws of nature exist. Right? What does it mean, laws of nature? So there must be some statements which are universal in a sense. They are applicable in many situations. So this is this universality, and somehow took into account some very special properties of the actual or determinants of the actual situation. So he says that, for example, free fall of bodies does not depend whether they are thrown by men or women, and whether they are thrown in Pisa or whatever, or in any other place on Earth. Okay, and it is also very astonishing. Why some of the determinants of the actual situation are important for physical laws, and some are completely unimportant. So this is also a miracle that such laws exist. Okay, that they do not change. That the free fall does not depend on the place where we perform the experiment, or whether or does not depend on who actually performs this experiment. So this is also somehow miracle. So now the problem is, how does it work? It's also not clear, okay? So the main mystery is that the mathematical formulation of the physicist, as he says, as Wigner says, crude experience. So if we formulate this in mathematical terms, so we can make an amazingly accurate description of a large class of phenomena. So usually it goes like it goes in this way, that we first apply this mathematical concepts to some very simple idealized models or some very restricted class of phenomena, and then extend or try to extend this to the much wider class of phenomena. And then astonishingly, it works. It works, for example, and he gives three examples. Two of them are very, I would say, often quoted. So this is Newton's theory of gravity, in which this idea of free fall, I would say, was extended to the motion of moon, say, just by intuition, in a sense, which give rise to the theory of the theory of gravitation by Newton, the theory of gravity. And the second example is quantum mechanics, in which the the original ideas of Heisenberg and Jordan were first applied to a motion of a single particle, okay, when you substitute for momenta at positions the appropriate matrices, and then attempts to apply it to more complicated systems like atomic collisions or something like astonishingly lead to very accurate prediction. So this is how it works. There are also some other questions which are connected to this miraculous work of mathematics and physics, that there is no guarantee that it will always work. For example, it's already stated by Wigner in his paper that all attempts to make a unified mathematical theory which will somehow unify quantum mechanics and general theory or relativity failed, okay, until now. So we believe that it is possible, but as Wigner points out, there is no guarantee that something like that will happen, okay? So what are the conclusions? Well, conclusions are that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. And the second conclusion is that we should be grateful for it and hope that it will remain valid for in future research. So that, for example, that we finally find this unique theory of gravity and quantum mechanics. Okay, at the very end, let me mention some other, maybe not other, but other point of view on mathematics, mainly that mathematics is a part of physics. So I start with a quotation from Vladimir Arnold, prominent mathematicians of 20th century, Russian mathematician, who said that mathematics is a part of physics. Physics is an experimental science, a part of natural science. Mathematics is the part of physics where experiments are cheap. You do not need very complicated equipment to check the validity of some physical statement. You simply perform mathematical experiment, okay? And this is also an experiment. And the second statement by Arnold is that the scheme of construction of a mathematical theory is exactly the same as that in any other natural science. First, we consider some objects that make some observation in special cases. Then we try and find the limits of application of our observation, look for counterexamples which would prevent unjustified extension of our observation onto a too wide range of events. So this is exactly what was also in Wigner, so that we start from very simple and probably idealized concepts and situations, and then try to extend it further and further and check whether it works. And what is pointed also by Arnold, that it is that mathematics is a part of physics, and this is very important because he quotes also he attributes this to another mathematician, Russian mathematician, famous mathematician Gelfand, that there exists yet another phenomenon which is comparable in its inconceivability with inconceivable effectiveness of mathematics in physics noted by Wigner. This is equally inconceivable in ineffectiveness of mathematics in biology. So in physics it works, in biology usually it does not work. Okay, so this is some special intimate connection between physics and mathematics, and this connection is that physics is a part of mathematics is a part of physics. So in my formulation, I will attempt to understand this the following way, that mathematics really is an experimental science, a part of physics. Physics is an experimental science. And the experiments are performed in mind on ideas abstracted from physical reality. So, using the language of Immanuel Kant, it produces judgments that are synthetic and a priori. Synthetic means that this new statements or judgments give some new information to our knowledge. So there is a real input to our knowledge. This is not, I would say, something which is contained already in the definition, of an concept. Okay. And a priori, because we do not need an experiment in physical reality to be sure that they are true. So, and this is this vision of mathematics which I entertain very much. Okay, so this is really an experimental science in our mind. Okay, so thank you very much. As I tried to be very concise, but didn't succeed too much, but we still have something like 10 minutes for discussion and questions if they are some.